Hello and welcome to day 2 of integration by parts. Integration by parts twice. As the name implies, we're going to be required to do integration by parts twice to evaluate one integral. In fact, we might just generalize and say that we could do integration by parts repeatedly in order to evaluate an integral. But our first example is going to require doing integration by parts twice. Because the method is not really different than integration by parts, but rather just using it twice in one problem, I'm going to start right off with a problem to demonstrate. This is example 3 in your notes. Remember, with integration by parts, we are going to think of the integral as the integral of the product of a function and a derivative, which we have a formula for. And we make choices for u and dv, and hope that it works out. Having done only 1 or 2 problems, you may or may not feel like confident that your choices will be the best choices for u and dv. But it gets easier as you get clued in on what integral you'll be left with. As soon as you decide on what u and dv are, and then actually find du and v. Here, v must have been negative cosine of x. U dv, du, and I found v. It's required integrating my choice for dv. You have to be able to do that. Anyway, using my formula, I know that this integral is equal to x squared times negative cosine of x. That's uv minus the integral of v negative cosine of x du times 2x dx. We'll rewrite that a little bit. Okay. Now, none of my previous methods allow me to integrate 2x cosine of x dx, but it does look like an integration by parts problem. In fact, integration by parts won't evaluate this integral. So we'll start all over with integral of 2x cosine of x dx as if it were my original problem, and I'm choosing u and dv as factors of this. So these are different u and v down here that I'm using to evaluate this integral, which will allow me to finish my original problem. I'll let u equal to 2x, and du equals to 2 dx. dv I will let equal to cosine of x dx, then v must have been the sine of x. That function, which I would take the derivative of to get cosine x. Okay, plugging these into the formula, I get uv, which is 2x sine x, minus the integral of v du, still using this formula. I think that's going to be 2 sine of x dx. Okay, this is an integral I can do by inspection. I believe that negative cosine is the function I differentiate to get sine of x. So I'm going to call this There is a C here, of course, but as long as we add it at the end, we don't really need to write it down every time. Okay, so now I have used integration by parts to find this integral, which I'll plug into here, and then I'll be done with this original problem, and I can say the integral of x squared sine of x dx is equal to original uv plus the integral of 2x cosine x, which I used integration by parts to find. And so I was able to find the integral of x squared sine x dx by applying integration by parts twice. When I applied it the first time, I was left with an integral which required integration by parts to do. I did integration by parts to evaluate that second integral, and then took that value and plugged it back in my formula for the integral of the original, or that I was originally trying to solve. You could take the derivative of this function to verify that it is in fact the antiderivative of x squared sine x dx. Now I'm going to stop, and I'm going to make a separate video for example 4.